Okay, so yesterday we had done a confidence interval to try and estimate the difference in two population proportions. Today we're going to continue on, or in this video, we're going to continue on with looking at differences in population proportions, but now we're going to run a test of significance. So we're going to look at this question here that begins with the word researchers. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in two low-income elementary schools. An SRS of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not had breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions? Carry out a test at the level of significance equal to 0.05 to support your answer. So clearly they asked for evidence, so I know that that means they want me to carry out a hypothesis test. And so of course I'm going to begin with my state. Now in my state, I need to write down all of my parameters and statistics, and also, because it's a test, give a ho and a ha. So let's see, my p-hat for School 1 is 19 out of 80, and my p-hat for School 2 is 26 out of 150. I'm wanting to estimate the difference in these populations, not estimate, see if I have evidence to show that there is a difference in these population proportions. So the parameter that I'm going to define is the difference in my p's, okay? And of course that needs to be defined in context. I was also told that the populations of both of these schools are at least 1,500. And we know that that's going to be important when it comes time to check for independence. So here I have my state, okay? I've included my p-hat from School 1. I've included my p-hat from School 2. What was a little unusual in this one is that I told you that the populations were bigger than 1,500, so I included that. And then I also have stated a null and alternative hypothesis. Now notice that all I've said in the null is that there is no difference in these population proportions. So I've said if I subtract p1 minus p2, I'll get a difference of 0. The other way you could write that would be just to say that p1 is equal to p2. Okay? They did not specify a direction if they thought one school had a larger proportion of kids that come without having eaten breakfast than another. So they just said, is there evidence of a difference? So it's a two-tailed test. That could be written as p1 is not equal to p2. So you can choose to write it in either way. Okay? And of course I need to define my p. So my claim is being made about the difference between these two proportions. So I've defined p1 minus p2 to be the difference in the proportion of students at these two low-income schools that have not eaten breakfast. So now I move on to my plan, and just like our confidence interval yesterday, we need to check for independent random. We need to also check for normality, and then we need to check to be sure that within each population from which I selected my sample, I have independence, that taking that sample out of that population has not changed the distribution of those students that remain in the population. So I did check those very same things that we did in our confidence interval yesterday. So independent random, I think it's reasonable to assume that the kids at one school don't affect the kids at the other. Normality, notice I'm checking my NP and NQ for the first school, and I'm checking my NP hat, I should say, and NQ hat for the students at the second school. And I was told that there were more than 1,500 students at School 1, so that's bigger than 800, and that there were more than 1,500 students at School 2, so that's just barely the right size. Okay? So it's reasonable to assume that these samples have been taken from those populations and that they are independent of other samples that could be taken. So there's my plan. Now, we know with confidence intervals, every confidence interval has a basic model, and that is take a statistic plus or minus a critical value times a standard deviation. But we're doing a hypothesis test. So all hypothesis tests have a basic test statistic formula. You take your statistic minus your parameter, and you divide by your standard deviation of your statistic. So we come down here to our two sample procedures, and our statistic we clearly see here is the difference in our sample proportions. So that's going to be our p hat 1 minus our p hat 2. Our parameter is what we claimed was true of the difference in the population proportion, so it's 0. And then our standard deviation of the statistic we see is one of these two standard deviations. Now yesterday we added the variances and square rooted to get the standard deviation for a confidence interval. But with hypothesis tests, we've made the claim that P1 is equal to P2, and therefore we use this standard deviation formula here. This is called a pooled p-hat. And I promised to explain a little bit more about why we pool our p-hats in a class together on Monday, okay? But we're going to pool our p-hats. So this is pooled p-hat, pooled q-hat, and then these, of course, are the two sample sizes. So, in my do here, I'm going to plug in all of that information. So again, you take your statistic, and by the way, this is Z for proportions, of course. The statistic is the difference in our p-hats. You subtract your parameter, and in the null hypothesis, we have said that that parameter is equal to 0. So we're just basically subtracting 0. And then we divide by our standard deviation of that statistic, which is the pooled p-hat, q-hat square rooted times the square root of 1 over the first sample size plus 1 over the second sample size. Now the other way that the standard deviation can be written is you can just put them all under one radical. You can just say p hat q hat times 1 over n1 plus 1 over n2, and then square root that answer. And again, we'll explain why, because that's a rather somewhat lengthy discussion or explanation as to why we pool with hypothesis tests. Okay? Now, the question now is, how do we get that pooled p-hat? Well, a pooled p-hat is where you basically just pretend that you haven't taken two separate samples, but rather you just took one big sample from one big population. Okay? So what the basic thing you're doing is you're taking the number in the first sample who had not eaten breakfast, and you add the number in the second sample who had not eaten breakfast. Okay? You then divide that by the total number of students selected. That's the sum of our two sample sizes. That's a pooled p-hat. So the number in our first sample that had not eaten breakfast was 19. The number in school 2 that had not eaten breakfast was 26. The number selected total from school 1 was 80. And the total number of students randomly selected from school 2 was 150. So our pooled p-hat here is going to be 45 out of 230. And for just to make it easier, when I get to the do, that is equal to about 0.196. Okay? So now what do we do? Let's plug in all of our numbers. So z is equal to p hat 1, which was 19 out of 80, minus p hat 2, which was 26 out of 150, minus 0, of course, doesn't affect that, all over the square root of our pooled p hat, which was about 0.196, times 1 minus that, which would be about 0.804, and then times 1 over the first sample size plus 1 over the second sample size. Thankfully, we will not have to type this in ourselves. We're going to go to our test menu and have it get it for us. Okay? So this is what your calculator does, though, when it is finding z. Okay? So I'm going to go and find this two-proportion z test. I want to name it. Okay, two-proportion z test. So if I go to my stat test menu, stat test, two-proportion z test is option 6. X1, how many in my first school did not eat breakfast? 19. N1, there were 80 selected. X2, the number in my second school that had not eaten breakfast was 26. N2, 150. Did I say that P1 is not equal to P2? I did. So I'm going to hit enter there. This is a two-tailed test, so if I draw, I'm going to see two tails shaded. My z-score was 1.17-ish, so my sample results were actually up here, okay? But because it's a two-tailed test, then we have to go 1.17-ish standard deviations below, and so your p-value is the area of both of those tails together, okay? This is a less powerful test because it's harder to reject the null in a two-tailed test because of the fact that you take whatever the area is in the tail for your sample results and you have to double it because of the fact that it could be in either tail, you weren't sure. So I'm going to record my z of 1.17, and that gave me a p-value of about 0.2427. Is that unusual? Not at all. I'm going to fail to reject the hoe because my p is so large. Okay? So in conclusion, we have to have three things. What's our decision about the null? So I'm going to fail to reject the hoe. Second, why have I made that decision? Because p is so large. Third, now say in context what you believe about the alternative. We do not have evidence to say that the difference to say that there is a difference between the proportion of students in schools 1 and 2 who come to school hungry. There is your first two-sample hypothesis test. Obviously, it's a hypothesis test about the difference in proportions. What we'll be doing next week is looking at hypothesis tests about the difference in means as well as their corresponding confidence intervals. So have loads of fun working on those frappies, and I look forward to reconnecting with you guys again on Monday.